Welcome back. In last week's lecture, we introduced vectors and then we extended the concept to talk about parametric vector equations of lines. In lecture today, we're going to talk about dot products and then also equations of planes using vectors. For our warm-up today, we're thinking back to at the end of Calc 1 when we first introduced work. So how much work is done in lifting a 50-pound box of books from the floor onto a shelf that's 3 feet high? Work is force times distance. And in this case, our force is constant, so 50 pounds. And we're lifting the books 3 feet high, so our distance here is 3 feet, which gives us that the work is 150 foot-pounds. So now, how much work would be done by a force, 8I minus 6J plus 9K, which we're measuring in newtons, to move an object from the point 0, 10, 8 to the point 6, 12, 20 along a straight line, which we'll measure in meters. Instead of thinking distance now in terms of vectors, we want to think displacement. So our displacement vector, which we'll call capital D, is equal to, we can do 6 minus 0 in our x component, 12 minus 10 in the y component, and 20 minus 8 in the z component, which simplifies down to 6 to 12. How can we find the work done, which is a scalar, when our force and our displacement are both in terms of vectors? We need some other idea that introduces this idea of multiplication, but in the context of vectors. And we call that the dot product. So algebraically, the dot product takes two vectors and it returns a scalar. In n dimensions, for some vector u, you take your u1, u2, u3, dot, 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 u sub n, and the dot product of that with v1, v2, v3, dot, 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 vn is u1, v1 plus u2, v2 plus u3, v3 plus dot, 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 all the way up to un, vn. And notice that this returns a scalar back to us. From our previous example, we have work is equal to the dot product of our force vector and our displacement vector. Our force from the previous page, the vector was 8, negative 6, 9. And we found our displacement vector to be 6, 2, 12. To compute that dot product, we take the product of the x components, so 8 times 6, plus the product of the y components, negative 6 times 2, plus the product of the z components, 9 times 12. Simplifying, 8 times 6 is 48, minus 12, plus 108. That simplifies down to 144 Newton meters or joules. What else can we do with the dot product? Algebraic properties of the dot product. Let's say that we have three vectors, u, v, and w, and we're in Rn. So we don't have to be in 2 dimensions or 3 dimensions, but rather n dimensions, and then for some scalar c. U dot v is equal to v dot u. This is the commutative property. The distributive property also works over vector multiplication, addition, and subtraction. So those are your next three properties. For the last one, we have u dot u. Let's do a quick little proof here to figure out what that is equal to. We're not going to restrict ourselves to 2 dimensions or 3 dimensions. We'll stay in Rn. The dot product of our vector u, which is u1, u2, dot, 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 u sub n. And we're taking the dot product of it with itself. So u sub 1, u sub 2, all the way up to u sub n. We add the products of each of the components. So u1 times u1 plus u2 times u2 plus dot, dot, dot plus u sub n times u sub n. And u sub 1 times u sub 1, that's u sub 1 squared, plus u sub 2 squared, plus dot, 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 plus u sub n squared. From our distance formula, or our magnitude formula from last week, we know that this is equal to the magnitude of the vector u squared. Geometrically, the dot product gives us the angle between two vectors u and v, assuming that the two vectors are starting at the origin, or another way to think of it is that they're tail to tail. And we're also restricting the angle between the two vectors u and v to be between 0 and pi. In that case, then the dot product is equal to the magnitude of u times the magnitude of v times cosine theta. And I've included a proof of the property below so that you guys can read over it on your own. But for the sake of time, I'm going to move on to our next example. Let's find the angle between the two vectors, u equal to 4, negative 2, 1, and v equal to 3, 1, 3. To find the angle between the two vectors, let's start by finding u dot v. U dot v is equal to the dot product of 4, negative 2, 1, and 3, 1, 3. So then we'd have 4 times 3 plus negative 2 times 1 plus 1 times 3. That simplifies to 12 minus 2 plus 3, which is 13. To find the magnitude of u, that is equal to the square root of 4 squared plus negative 2 squared plus 1 squared. 4 squared is 16, plus 4 is 20, plus 1 is 21. So we have the square root of 21. And the magnitude of the vector v is equal to the square root of 3 squared plus 1 squared plus 3 squared, which is the square root of 19. So then, using our formula and solving for cosine theta, we have that cosine theta is equal to the dot product, so u dot v, which is 13, divided by the magnitude of u, square root of 21, times the magnitude of v. It's the square root of 19. And to get a decimal approximation for theta, we find that theta is equal to approximately 0.8621 radians, or in degrees, theta is approximately 49.4 degrees. So for your work, you want to show both your formula for cosine theta and also your decimal approximation. By default, we usually use radians, but in this case, sometimes it maybe makes more sense to think of this as degrees. So you can use either radians or degrees. Just make sure that in your answer, you're labeling whichever one that you're using. Okay, so let's do one more. Let's find the angle between the vectors u equal to 4, 3, 2, and v equal to 3, negative 2, negative 3. So u dot v is equal to 4 times 3 plus 3 times negative 2 plus 2 times negative 3, which is 12 minus 6 minus 6, which is equal to 0. The magnitude of u is equal to the square root of 4 squared plus 3 squared plus 2 squared. So we have 16 plus 9 is 25, plus 4 is 29, so the square root of 29. The magnitude of v is the square root of 3 squared plus negative 2, quantity squared, plus negative 3, quantity squared. 9 plus 4 is 13, plus 9 is 22, so the square root of 22. Cosine theta is equal to u dot v, which is 0, over the magnitude of u, the square root of 29, times the magnitude of v, which is the square root of 22. Because of that 0 in the numerator, we end up with cosine theta is equal to 0. And so solving for theta, that tells us that theta is equal to pi over 2 radians. If you want to be in degrees, we could say or 90 degrees. This is always going to be true anytime that the dot product between two vectors is 0. The angle between them has to be pi over 2 or 90 degrees. And so we can say that u dot v is equal to 0 is the same if and only if the vector u is perpendicular to the vector v. This can be a pretty handy theorem for us to have. Now we know that two vectors are perpendicular if their dot product is 0. And from last Wednesday, we knew that two vectors are parallel if and only if one of the vectors is a scalar multiple of the other vector. In the example below, let's determine if the vectors are parallel, perpendicular, or neither. Starting with part A, we notice that if we take our vector u and we divide through by 2, and then we multiply through by -3/2, then we get v. And so since -3/2 u is equal to our vector v, then we know that our two vectors must be parallel. In the next part, part B, looking at our signs, we notice that u is all positive, and we know that v is negative in the y component. And so there's no number that we can multiply through by u to get back v because the signs don't line up. So u and v are not going to be parallel. But let's look at their dot product. The dot product of 1, 2, 3 with 6, -6, 2. And that gives us 6 times 1 plus 2 times -6 plus 3 times 2, which is equal to 6 minus 12 plus 6, which is 0. And so since the dot product is 0, that tells us that our vectors u and v must be perpendicular. In the next example, part C, again looking at the negative in the y component of u, and in v, there's a negative in the y and the z component. So we know right away, just because the signs don't line up, that these two vectors are not scalar multiples of each other. There is no c such that u is equal to c times w, and so they are not parallel. And looking at the dot product of our two vectors, u dot v is equal to 2 times 3 plus -4 times -6 plus 6 times a -9. And that simplifies down to 6 plus 24 minus 54, which is a -24. That tells us that the two vectors are not perpendicular. So u is not going to be orthogonal or perpendicular to the vector v. And so in this case, they're neither. But now note, if we were going to find the angle between these two vectors, the magnitude of u, that is going to be equal to the square root of 56, which you can reduce down to 2 root 14. And the magnitude of v, that is equal to 3 root 14. And so cosine theta is equal to our negative u dot v over 2 root 14 times 3 root 14. And that simplifies down to -2/7. And then if we solved for theta, we would find that theta is approximately 106.6 degrees. Notice that since the magnitudes of u and v are always going to be positive, The only thing that will make cosine theta equal to a negative value is if the dot product is negative. U dot v is less than 0, and when we were defining the angle between two vectors using the dot product, we had that restriction that theta was going to be between 0 and pi. And so that tells us then, if theta is restricted between 0 and pi, that with a negative cosine theta, that's only going to happen if our dot product is less than 0. And that's only going to happen if the angle between u and v is obtuse. So just a nice handy little fact to help you check your work and make sure that the answer you get makes sense, that if you have a negative dot product, then you should find that the angle between the two vectors is obtuse, and then if you have a positive dot product, then the angle between the two vectors is going to be acute. For any two vectors u and v, there exists a unique pair of vectors, which we call u parallel and u perpendicular, such that u parallel runs along the vector v, u perpendicular is perpendicular to v, and also u parallel plus u perpendicular is equal to the vector u. U parallel and u perpendicular is notation that you'll see in other books. It can be rather handy, but for us, we will call u parallel the projection of u onto the vector v. And the magnitude of the projection of u onto v, we call that the component projection of u onto v. And that is the magnitude or the length of the projection vector. Then u perpendicular, we denote that as the orthogonal projection of the vector u onto v. And if you look above, where we have that u parallel plus u perpendicular is equal to the vector u, if we solved that for u perpendicular, or the orthogonal projection of u onto v, then we would have that is equal to the vector u minus the projection of u onto v. Geometrically, we can think of the projection of u onto the vector v as the shadow of our vector u on the vector v, thinking if the light source is perpendicular to the vector v. In the first one that I've sketched here, if you were to draw the projection of u onto v, you would want to start by thinking of your light source as being directly above the vector v. And then you would drop a perpendicular line down from the vector u onto the vector v. That tells you where to draw the projection of u onto v, or rather the magnitude, since it runs along the vector v, and its length will be from the tail of u to the base of the perpendicular line. Let's do another one. Notice that the vector u, while we're projecting it onto v isn't long enough for the projection to hit the vector v. In this case, just extend the vector v, draw a line parallel to v, and now you can drop a perpendicular line from u onto the vector v. And that tells you how long to draw the projection of u onto v. For the last one, where our angle is obtuse, if we were to draw a perpendicular line starting at the head of u and then falling onto v, we need to extend this vector v. So we draw a line extending out the vector v in the opposite direction, so that now when we drop a perpendicular line from u, it hits our parallel line to the vector v, and that gives us our projection of u onto v. So geometrically, whenever you're sketching this, just think of your light source as being perpendicular to the vector v. Algebraically, though, to find the vector projection of u onto v, start by drawing a right triangle by dropping that perpendicular line down. Then we know that cosine theta, where theta is the interior angle between u and v, is going to be equal to the projection of u onto v over the magnitude of the vector u. Multiplying both sides of our equation through by the magnitude of the vector u, we have that the projection of u onto v, the magnitude of this vector, is equal to the magnitude of u times cosine theta. And then doing a little bit of tricky algebra. We're multiplying by 1 here, the magnitude of our vector v divided by the magnitude of the vector v, and using our property that the magnitude of u times the magnitude of v cosine theta, that is now our numerator, and that's equal to u dot v. So we have u dot v over the magnitude of the vector v. We call that the component projection of u onto v. We need this because we use the magnitude of this vector in order to find a formula for the projection of u onto v. Remember that our vectors have both magnitude and direction. Well, the magnitude is what we just found. So that's our u dot v over the magnitude of v. And the direction of our vector, the projection vector, will always lie along v. So the unit vector of v gives us the direction of our projection vector. Simplifying, we have in the denominator the magnitude of v times the magnitude of v, quantity squared, and in the numerator u dot v, and then times our vector v. Knowing that our projection is parallel to the vector v, and the coefficient of our vector v is u dot v over the magnitude of v squared, so this is a scalar, times the vector v. And that gives you the formula for your projection of u onto v. Since we're projecting u onto the vector v, we're going to be laying along the vector v, and notation-wise with the subscript of v, thinking that u is bigger than or lying on top of vector v. Let's find the projection of our vector 2i plus 3j onto the vector b, which is equal to 5i plus j. To find our projection vector, let's start with our formula so that we have it in terms of our vectors a and b instead of u and v. We have the projection of a onto the vector b. If we were to sketch that very roughly, it would look something like that vector. That is equal to a dot b over the magnitude of b squared. And since our projection lies along the vector b, then we are multiplying this by our vector b. This is equal to, we have a dot b, 2 times 5, plus 3 times 1, over the magnitude of b squared. So that would be the square root of 5 squared plus 1 squared, and that entire quantity squared. And then we're multiplying that by our vector 5i plus j. Simplifying the dot product, we have 10 plus 3. 10 plus 3 is 13. And in the denominator, 5 squared is 25, plus 1 is 26, and the square root and the square cancel out. And times our 5i plus j. Simplifying, 13 over 26 is 1/2. 5i plus j. You can distribute that 1/2 if you want, but it's also okay to leave it in this form. So when you're finding these projections, it is important which vector you're projecting onto the other. And so in example 6, you're asked to find both the projection of b onto a, the first one, and then here we have the projection of a onto b. I'm going to leave this to you for the sake of time to do on your own, but I did give you the answers to check your work, but make sure you know which answer lines up with which of the projections. And then we'll get a chance to do this some more tomorrow in workshop as well. Last week, we were able to find a formula for the parametric vector equation of lines in R3. So today, we can take that idea and extend it to finding equations of planes. To uniquely define a plane in R3, we need 3 points that are non-collinear that lie on the same plane. Or from those 3 points, we could use those 3 points to find 2 vectors that are parallel to the plane but not each other. Or we can go one step further and we can say that if we had 1 point on the plane and a vector perpendicular to the plane, then we could use that to define an equation of the plane. For example, if you imagine I have this sheet of paper and a vector that's perpendicular to the plane, then if we know the point where the vector that's perpendicular to the plane is touching the plane, then we can have a unique equation for the plane. So that's the idea behind it. So let's say that we have a normal vector to a plane that is perpendicular, normal meaning orthogonal or perpendicular to the plane, and then a point x naught, y naught, z naught on the plane through which the normal vector is going. And so then x, y, z is any point on the plane. So if we were then to draw the vector x minus p, connecting our point x, y, z and the point p into a vector, this would be our vector x minus p, then that vector, it lies in the plane, but it must be orthogonal to the normal. And so now we have two vectors that are orthogonal, and we know that two vectors are orthogonal if and only if their dot product is 0. Algebraically, we could write this as our normal vector n, its dot product with the vector x minus p, and that dot product must be 0 in order for the normal vector and the x minus p vector to be orthogonal. And so, since we know that the normal vector has the equation ABC, substituting that in, and taking its dot product with x minus x naught, y minus y naught, and z minus z naught equal to 0, simplifying, finding that dot product, then we would have a times x minus x naught plus b times y minus y naught plus c times our z minus z naught equal to 0. And so that gives us the normal equation of a plane, which is containing the point x naught, y naught, z naught, and normal to the vector a, b, c. Let's do an example. Let's find the normal equation of a plane that's containing the point 3, negative 4, 5, that is perpendicular to the vector 2, negative 1, 6. We know the equation of a plane is going to be the dot product between the normal vector and x minus p, where p is a point on the plane. And so in our case, we have the normal vector 2, negative 1, 6. And we can call our vector p, which would be OP, where O is the origin, 3, negative 4, 5. Taking the dot product of our normal vector 2, negative 1, 6, with x minus our x naught, 3, y minus a negative 4, and z minus 5, and that is equal to 0. Taking that dot product, we get 2 times x minus 3 minus 1 times y plus 4 plus 6 times z minus 5. And that's equal to 0. It's okay to stop here. You do not need to simplify this fully. In the next example, let's find the normal equation of the plane that contains the point 2, 1, negative 3, and that is parallel to the plane 3x minus z equal to 7. Parallel planes are going to have parallel normal vectors. And so here, the equation of the normal vector is 3, 0, negative 1, and our point in vector form is p equal to 2, 1, negative 3. And so the equation of our plane is going to be 3 times x minus 2 plus 0 times y minus 1 plus a negative 1 times z minus a negative 3. And that is equal to 0. And that's it. That is the equation of your plane, and you don't have to simplify that. And I did show the 0 in the y component just so you could see where the equation was coming from. In example 9, let's find the normal equation of a plane that's containing the points A, B, and C. We can find two vectors. We could use these points to find vectors, but we don't have any way of finding the normal equation of the line. And so we need another tool at our disposal in order to find that normal vector, which is what we'll talk about in our next lecture. In our last example, let's find the shortest distance between the point 1, -2, 4, and the plane 3x plus 2y plus 6c equal to 5. And I'm going to show you two different ways to do this. So in the first way, notice that the shortest distance between the point and the plane is going to be a line that is orthogonal to the plane. We also know that the line orthogonal to the plane is the same as the normal vector of the plane. So let's use our normal vector, which is 3, 2, 6. Let's begin by finding the equation of the line that is parallel to our normal vector n and through the point 1, -2, 4. We have our direction vector n, our point p, and so the equation of this line is r of t equal to p plus dt. So p is 1, -2, 4, plus, using our normal vector as our direction vector, we have 3, 2, 6 times t, which we can also write that as 1 plus 3t, -2 plus 2t, 4 plus 6t. The point of intersection between the line and the plane, let's label that as our point of intersection, which we know how to find from our previous example. We will take our x component of our line and sub that into the equation of the plane for x, and then likewise for our y component and our z component. And then we'll use that to solve for t. The intersection of our line, r of t, and the plane is 3, and then in place of x we have 1 plus 3t plus 2, subbing in for y, -2 plus 2t, plus 6, and subbing into our z component, we have 4 plus 6t, and that's equal to 5. Distributing, we have 3 plus 9t minus 4 plus 4t plus 24 plus 36t equal to 5. Looking at our terms with a t in it, we have 9t plus 4t is 13t plus 36t, so 13 plus 36 is 49t. And that is equal to 3 minus 4 is -1, plus 24 is 23, and 5 minus 23 gives us -18. Solving for t, we get that t is -18 over 49. So then to find the point of intersection between the line and the plane, we sub that in for t into r of t. We're subbing in here for t. Let me change that to our -18 over 49. And then simplifying algebraically, we get -5 over 49, -134 over 49, and then 88 over 49. Now we have the point that lies in the plane, and our point 1, -2, 4, And so we want to find the distance between the two. And our given point P. Subbing those into our distance formula, we get that our distance is equal to 1 minus negative 5 over 49 quantity squared plus negative 2 minus negative 134 over 49 quantity squared plus 4 minus 88 over 49 quantity squared. And that is equal to 1 minus the negative 5/49. That simplifies to 54 over 49 squared plus, in our y component, we have 36 over 49 quantity squared plus, and then 4 minus 88 over 49. That simplifies down to 108 over 49 quantity squared. Squaring it and combining, we get the square root of 324 over 49, which is equal to 18 over 7. Not too terrible, but not too easy either. The algebra in here actually takes a little while to compute and simplify it all down, so a little bit of work there. But I also wanted to show you a shorter and easier way to find this distance between the point and the plane. Let's start by drawing our normal vector. Our normal vector is the vector 3, 2, 6. And now let's find a point in the plane. I'll call it Q. And you can find any point as long as it lies in the plane, so as long as it satisfies the equation 3x plus 2y plus 6z is equal to 5. And noticing that we could let x equal 1, y equal 1, and z equal to 0. A nice easy point to work with. Then the vector QP. We will both sketch it and find it algebraically. So QP looks like this. And algebraically, QP is equal to the point P minus Q, the 1, 1, 0 above. And so we have 1 minus 1 is 0. In the y component, we have negative 2 minus 1. And then in the z component, we have 4 minus 0. If we look at the projection of the vector QP onto the normal vector n, then that projection vector is going to look something like this. If I can sketch it in quick for you. And so the distance between the point in the plane and our given point P, that shortest distance is now going to be the magnitude of the projection vector. So in orange here, that was our projection vector of QP onto our normal vector n. Okay, so the magnitude of that is our component. So we want the absolute value since we're dealing with a distance. We want our distance to always be positive. So the absolute value of the component of qp onto the vector n. Okay, just make a little side note here that the first set of absolute values, we're talking about the magnitude of the projection, which is the component, and then we want the absolute value of that. So maybe I'll put another set of absolute values out here. So it should follow a little bit easier now. Okay, so the component of qp onto our vector n is equal to absolute value of n, the dot product of n with qp, divided by the magnitude of n. We have the absolute value. When we take the dot product of the normal vector with qp, we have 3 times 0 plus 2 times negative 3 plus 6 times 4. And that's divided by the magnitude of the normal vector, so the square root of 3 squared plus 2 squared plus 6 squared. And so in the numerator, we have 0 plus a negative 6 plus 24, which is positive 18. And then divided by the square root of 9 plus 4 is 13, plus 36 is 49, and the square root of 49 is 7. So algebraically significantly easier if we use the component of the vectors qp onto the vector n rather than finding the equation of a line and then finding the point of intersection of the line and the plane and then finding the shortest distance between the point of intersection and the given point. So either way works, but definitely this is just a nice application of the component vectors.